Welcome. My name is Marco Mangano, and I'm a PhD student at the Multidisciplinary Design Optimization Laboratory at the University of Michigan Aerospace Engineering Department. In the next few minutes, I will present the work that my colleagues and I submitted for the 2022 SADC conference, focused on the aerostructural design of large wind turbine rotors using high-fidelity multidisciplinary design optimization. The main goal of this paper is to demonstrate that high-fidelity multidisciplinary design optimization, or MDO, is a viable and effective approach to support the design of modern wind turbines. In the next few slides, I will first introduce MACH, the high-fidelity optimization framework developed at our research lab, and then the benchmark models that we use as initial design configuration. I will then explain the formulation of optimization problems in terms of objective function, constraints, and design variables, before giving a few remarks on the modeling assumptions of our approach. In the results section, I will first go over a loosely coupled approach that uses single-discipline structural optimization for the preliminary sizing of the rotor. Having these results as a starting point, we will show how the tightly coupled aerostructural model brings quantifiable design advantages over the faster but simpler approach. Finally, we'll showcase more complex MDO cases where we use a broader set of design variables and explore different objective functions. The diagram in this slide illustrates the components of our optimization framework. We have separate software modules that enable geometry manipulation via freeform deformation approach, a mesh deformation algorithm to propagate the geometry updates to the volume mesh, and the coupled aerostructural solver. We use pipe spars to wrap SNOpt and manage the information flow between the optimizer and other framework modules. In the aerostructural analysis block, we couple our run solver and our finite element solver using a conservative and consistent low displacement transfer module. We use the Gauss-Seidel algorithm to converge the two solvers until a steady-state aeroelastic solution is obtained. A key feature of this module is that it also provides coupled system sensitivities with respect to the design variables using the adjoint method. The computational cost of the adjoint solver does not scale with the number of design variables, enabling us to efficiently perform high-fidelity optimization with hundreds of structural, aerodynamic, and geometrical design variables. The optimization studies we discuss in this paper use the DTU 10 MW turbine rotor as initial design. Our work builds on the aerodynamic shape optimization studies that Madsen and others carried out using the open source version of MACH, named MACH Aero. We use the same FFD control volumes and aerodynamic meshes that have been verified in this previous work. As shown in the table at the bottom right of this slide, the computational cost of the CFD solution varies greatly depending on the refinement level of the meshes. For demonstration purposes, we use the less accurate but cheaper level 2 and level 3 grids in this work. The structural mesh has been developed from scratch for this paper. The outer skins match the outer mold line of the aerodynamic mesh, while the internal structure, consisting of a shear web and a trailing edge reinforcement spar, have been designed following the benchmark model description. We developed meshes with both composite and isotropic material properties, but only the latter will be used in the coupled optimization problems. In terms of structural parameterization, we assign a single independent thickness design variable to every color panel in the figure at the bottom of this slide. Although our framework has been extensively used for multi-point optimization problems, in this paper we consider a single inflow condition representative of the turbine power output. As described more in detail in the paper, this simplifies the efficiency and cost metrics to torque and rotor mass respectively. We consider these functions both individually and linearly combined in the optimization objective. In total, we have 117 of the independent structural design variables mentioned in the previous slide. For the full MDO studies, we also include 7 geometric design variables to modify the spanwise twist distribution. To ensure the structural feasibility of the optimized rotor, we enforce both stress constraints, based on the von Mises criterion, and maximum tip displacement constraints. These functions are evaluated element-wise and then aggregated over the blade components using the Kresselheimer-Steinheiser formulation. This reduces the number of output functions and ensures their smoothness for optimization purposes. Note that for mass minimization problems, torque is included as a constraint and not in the objective function. Now, before we dive into the results, I want to touch upon a few key modeling assumptions that characterize our optimization studies, some of which will be addressed in future extensions of this work. In the first place, our analysis is limited to the sole steady-state aeroelastic response. An unsteady approach is not implemented in MACH yet and will quickly become numerically untractable, among other issues. Moreover, we only consider the turbine rotor design, ignoring the mutual interaction between the rotor and the rest of the turbine. Conventional design tools use multi-body formulations to account for the structural response of the entire structure. The methodology we propose does not aim at replacing such tools, but rather complement them, offering higher design insight on system components. Unsteady and extreme loads are driving factors in the sizing of wind turbines. Another paper in collaboration with the Flow Lab at Brigham Young University, presented in the same session, addresses this design concern. We propose a methodology to include extreme and fatigue loads obtained with conventional tools within the high-fidelity approach we discuss in the present work. In the results section of the paper, we provide more detailed information on the coupled model we use, its numerical verification, and the overall computational cost of our optimizations. We first present our preliminary sizing approach based on a loosely coupled optimization strategy. We ran a sequence of structural design optimizations with frozen aerodynamic loads. These loads are updated between different optimizations using a standalone multidisciplinary analysis of the rotor with the updated structural layout. In this way, we partially account for the coupling between the structural displacement and the altered load distribution over the blades. Although less accurate, this approach is also less implementation heavy, while still providing relevant design intuition to the engineers. We estimate the effect of the different parameterizations and material properties on the thickness distribution, and quantify the impact of the displacement constraints on the final mass of the rotor. Due to the more conservative constraint enforced on this composite model, its overall weight is higher than its isotropic counterparts. In future works, we will focus on the composite model more specifically and add more design variables such as ply angles in the formulations. We use the results of these loosely coupled optimizations as a starting point for a structural sizing of the rotor using the coupled aerostructural model. For this set of results, we only use structural design variables and enforce a torque constraint. The case illustrated at the top of the slide refers to an optimization that, with respect to the initial point, maintains the same initial torque and allows for a 5% increase in maximum tip displacement. The optimizer is able to further reduce the mass of the rotor by 9.1% compared to the loosely coupled approach. Looking at the series of optimizations reported in the plot at the bottom, it stands out how even when we allow no increase in the tip displacement and maintain the same initial torque, the optimizer is still able to reduce the mass by more than 4%. In the paper, we discussed the effects of the constraints more in detail, but the key message of this optimization study is that the use of the coupled module leads to quantifiable benefits compared to the simpler, loosely coupled approach. Finally, we include both structural and geometrical design variables in the formulation and consider a linear combination of torque and mass in the objective function. This approach enables engineers to explore different design trade-offs that might depend on technological and economical considerations on the cost of energy models. Although more detailed result discussion is necessary to appreciate the design differences and select the most suitable configuration, the impact of the objective coefficients on the final design has an intuitive explanation. If the mass has small or zero weight in the objective, the optimizer will prioritize the aerodynamic efficiency and thus torque maximization. This might result in additional mass on the final rotor to ensure structural feasibility under heavier loads and lower tip displacement. Conversely, when for example torque and mass are equally weighted, the optimizer is able to simultaneously improve the aerodynamic performance of the rotor and reduce its total mass. The results we have just presented are preliminary and use simplified models, but strongly suggest how high-fidelity gradient-based optimization can be effectively used to improve the performance of wind turbine rotor and identify design trends to reduce the levelized cost of energy of wind power. In summary, we first demonstrated the advantage of using a tightly coupled physics system with respect to loosely coupled strategies, although this latter approach can still provide useful design insight with lower implementation and computational costs. The coupled agent approach enables us to run optimization cases with more than 100 design variables, as the optimizer is able to exploit blade steady-state aeroelastic coupling. Finally, we show our framework enables the exploration of a broad design space to provide designers detailed insight on the trade-off between mass and performance, as different cost of energy considerations are evaluated. We look forward to extend our studies to a more refined composite model and even a broader range of design variables. I invite you again to check out the work presented by Dr. Capras in the same session, where we address some of the shortcomings of our approach by adding low-fidelity informed sizing constraints based on fatigue and extreme loads. We would like to thank the Department of Energy ARPA-E for funding this research. The results shown in this paper have been run using resources from U of M Advanced Research Computing Center and the Texas Advanced Computing Center. Finally, I invite you to check out other interesting works presented by my colleagues from the MDO lab. Thanks for watching.